Hi, in this video I will show an example problem which is an electromechanical system. It has an armature-controlled DC motor. It has two inertias and these inertias are connected through a torsional spring. Both inertias are suffered or affected by two viscous dampers. They directly affect these dampers from the ground. Okay, so since it's armature-controlled DC motor, we know that it technically is affected from the feedback from the mechanical part. So what we can do is we can directly start writing the electromechanical conversion equations. Okay, we know that torque of S, we can write in the Laplace domain, is equal to Ka, a constant, times Ia of S, and I of S is technically the armature current, which is shown here. And we know that back EMF voltage is equal to, okay, some constant Kb, and the angular speed that's technically affecting, or that's technically measured at the motor shaft. In this case, this is omega m. So if we take the Laplace transform, it's equal to this. Okay, this is the first equation that we need to model this system. Okay, let's copy it. Let's cut it here. Okay, that's good. Okay, so now what we can do is we can start writing equations or move on with the equations of the electrical part. Okay, so again we can quickly write this in the Laplace domain. So we know that the voltage across these 2 points or the nodes is equal to VA of S minus EB of S. Okay, this is divided by the total impedance in these 2 points. Okay, RA plus S times LA, which is equal to IA of S. Okay, let's write this a little bit different. Okay, IA of S, which can be considered as the output of the electrical part, is equal to 1 over RA plus SLA times VA of S minus EB of S. Okay, so let's also copy this part. Okay, so let's paste it here. Do we have space now? So we can leave just here. Okay, that's nice. Okay, so we technically solved the electrical part. That's great. Okay, the critical part is the input is, of course, the main input of the system is armature current, armature voltage. But in order to affect the electrical circuit and generate the current, we need to have a feedback operation where we subtract VA from EB of S, which is critical in the block diagram topology that we will construct in this problem. Okay, that's nice. Now the mechanics. Okay, so the electrical motor generates a torque, okay, which directly affects the shaft of this Jm inertia. Okay, as you can see, it has an angular velocity, it has an angular displacement theta m. Okay, but we will not use direct the theta m in the equations. I will show you later. We will see that. Okay, and as you can see, this is also affected by the torsional spring. What we assume that since the electrical motor drives the disk or inertia of Jm, we assume that this torsional spring applies a resistive torque in the technically negative direction of the motion. Okay, this is an assumption. We can assume that it is like technically affecting the motion or driving the inertia. But what we do is we make an assumption and move on with our computations. In that respect, what we can do is we can write that Jm times omega m dot, okay, is equal to a minus bm beta m times omega m, or what I can do that, since they're in the same units, I can simply write it here. Beta m times omega m is equal to torque, which is the input torque that is driving the disk, minus the resistance torque kappa times, since it's resisting its motion, okay, we assume that it's in this direction, we assume that somehow theta m is greater than theta L. So let's write theta m minus theta L. Okay, so what we can do is this. Okay, we can write it in the Laplace domain. Okay, so technically S times Jm plus beta m times, okay, so let's write it like this, omega m S is equal to tau S minus kappa. I will write, instead of writing theta minus theta L, let's write it like this, theta, okay, difference S. Okay, so because it's a difference, so I can do that. If I need to separate them, I can separate them, but you will see that we will not need to separate them when constructing the block diagram topology. Okay, so let's cut it here. Okay, let's paste it here. Do we have a space? No, we don't have a space. Okay, that's nice. Okay, that's great. So we need this equations and that. Okay, that's great. So the only thing that we need to finalize is the equations of motion associated with the JL disk or the other inertia. Okay, so we assume that this torsional spring is applying a torque of this disk in this direction. So it's applying the torque in the other direction. Okay, because action and reaction, it's the principle. So we technically, in this sense, assume that this torsional spring is deriving the motion of the second disk. So in that respect, we can write that JL times omega L dot. So we know that we can quickly write it like this. Okay, L is equal to kappa times theta M minus theta L. Okay, that's nice, because we assume that theta M is larger than theta L, so it technically can then drive the motion. So let's write it in a simpler form. We know that omega L S is equal to 1 over JLS plus beta L times kappa delta theta S. Okay, so let's copy this and we will try to finish the block diagram topology using all of these equations. Okay, I can fit in here. Okay, so let's analyze this. What I need is, in these signals, if I technically rely on these equations, okay, so let's separate them. Okay, so separate them here. So I need torque. Torque depends on current. That's nice. I need angular velocities of M and L. That's nice. We had that. Voltage is the input. The output of the system, I didn't mention at the beginning, is the angular velocity. It's not the angular displacement of this disk. So we only need the angular velocity. And as you can see, we have delta theta S. Okay, what I can do is I can separate them and use theta M and theta L, which will bring some redundancy. I can still construct a block diagram, which will be a valid block diagram, but it won't be minimal. Instead, what I will use is this fact. Okay, so delta, okay, sorry for that, delta theta S is equal to the integral of the difference between the angular velocities. Okay, so it is equal to 1 over S multiply with omega M S minus, okay, omega L S. Okay, so what I will do is I will only use the difference between velocity, integral of difference between velocities. So I will not store or use the angular displacement of theta and theta independently. I will only use or store their difference in my variable. Okay, it's because we are using a torsional spring. It is a valid thing to do. Okay, so let's start directly building the block diagram. Okay, if you remember, okay, so let's write it here. Okay, that's nice. Okay, that's great. This is common. Okay, that's nice. It's not a big deal. So our input is VA of S, right? And if we take a difference operator where this is equal to EB of S. Okay, that's great. So what it is technically this. Okay, I know that. So this difference is the input of the electrical part, and this is my transfer function which produces the current. That's great. So what I can do is this. Okay, that's great. Okay, that's nice. So this is not good. I don't like this. Okay, so okay, that's great. So this is equal to 1 over, if you remember, LAS plus RA, which produces IA of S. Okay, that's nice. So this is check. So we use this equation. This is check. So current, and we also use this equation. So which one? Let's see. Okay, we also use this equation. So the torque is generated by the current, and we simply multiply with a constant. Okay, so what we do is, okay, we have a constant. Okay, so for that, okay, cut. We have a constant gain. Okay, that's great. Okay, this is equal to Ka, which produces the torque of S. I think that's great. Okay, so we are technically reaching somewhere from here. So we generated the torque. That's great. Okay, so we also use this fact. That's nice. So now what we can do is we can use this equation. Okay, so in order to produce the angular velocity, or omega m, okay, we need to take difference between torque with this variable. Okay, so we have a feedback or difference operation, and we need to multiply with the transfer function, which is equal to 1 over jms plus beta m. Okay, so what I will do is here, okay, this is nice, this is plus. Okay, I need to subtract it from a variable. I will do it later. Okay, and this will go to a transfer function block, which is equal to 1 over jms plus beta m, which produces omega m of s. I think that's great. Okay, so let's make it check. We only need this. Okay, it minus kappa times theta s. In order to generate that, I need to generate omega m and omega ls separately. Okay, and okay, that's great. No problem with this. Okay, so what I can use is the final fact. Okay, omega ls is equal to a transfer function multiplied with kappa times theta, delta theta s. Delta theta is equal to this. Okay, so what I do is here, I will do something. Okay, so if we have an input JLS plus beta L, we can generate omega L S. This is our output. Okay, so I have omega M, I have omega L. So what I can do is I can take the difference here if I want to do that. Okay, to obtain the difference. This is technically equal to this. Okay, this is theta s. Okay, so what I do is, if I have this quantity, as you can see, if I integrate it and multiply with kappa, I obtain this. Okay, as you can see, I need this operation, this quantity, both here and here. Here it is negative, here is positive. So if I do that in a simply fashion, okay, so this is kappa divided by s. So in integrator, multiply with a constant. Okay, so this is the angular velocity of this shaft. This is angular velocity of the output shaft. Its difference is technically this part is equal to omega m minus omega l. If I integrate it and multiply with kappa, what I obtain is, first I obtain the angular displacement, and I will multiply kappa, which is technically the torque of the torsional spring, which directly goes to the second shaft. Okay, so let's remember here, in order to obtain this operation, I need torque minus kappa times theta s, which is technically the quantity or the signal in this part. So if I do that, I finish the mechanical part. The only thing that I need to complete to finalize our block diagram is the back EMF voltage. So back EMF voltage is equal to simply Kb times omega ms. So I have omega m, which is here. So what I will do is simply, this is Kb. Okay, if I draw it here, I compute the back EMF voltage. Which I did is simply finalize the block diagram structure. So in general, drawing a block diagram, if you are careful, is slightly easier than computing the transfer function, and sometimes even the state space approach, because you need to come up with a topology of course, that can be hard, but at least computationally, you don't need to finance all of your computations. This is the advantage of the block diagram. If you live in a detailed framework, if it's a block diagram, you need less computations compared to other techniques. So it's also a representation of dynamical system, and as you can see, with less number of computations, we can finalize the block diagram topology. And you should be also noting the fact that there are no single block diagram representation. If you come up with a slightly different order of equations, slightly different approach, you can come up with different equal block diagram representations. Okay, so one of the advantages of this block diagram topology, which is here, okay, I will talk about now, is first of all, as you can see, all of the blocks are either a constant, okay, or they are a first order causal transfer functions. Okay, so it means that this is first of all a fully causal block diagram representation or block diagram topology. Causal means that we don't have something like S. Okay, so differentiator S block, we can do it when solving or simplifying block diagrams, but it's not causal. Okay. Second thing is, in this block diagram presentation, we don't have any higher order terms. Okay, why it's useful? It's useful if you want to find a state space representation directly from the block diagram representation, because it means that we can simply label some of the signals as our states and finalize the state space representation, which I will do in a second. Okay, so we finished the block diagram. As you can see, this is here. Okay, that's nice. So let's move it here. And then let's label some of the states direct on the block diagram. Okay, so first of all, these constants are just constants. They're not adding dynamics. They're changing the dynamics, but they're not adding an order or state to the system. Okay, the most natural choice for a block diagram representation which is fully causal and it's composed of only constants and first order transfer function blocks, okay, it's also included later, using the output of each transfer function or dynamic block as our state. So I assume that this is my first state, technically the current of the inductor or current of the armature circuit x1. Okay, this is my second state, okay, which is the angular velocity of the motor shaft. Okay, this is my third state, okay, x3, okay, which is technically the angular difference between two shafts multiplied with the kappa. Okay, that's nice. And my last state is my output, which is equal to x4. Okay, and as you remember, selecting your output as one of your states simplifies output equation, which is also nice. Now, using this fact and this block diagram topology, we will try to find the state equations. Okay, so let's start with x1. x1 of s is equal to 1 over LAS plus RA, okay, multiply with VA. VA is our input, okay, we know that, U of S minus EB of S. But EB of S is not a state, right? Instead, we write it like this, KB times X2 of S. As you can see, X1 in Laplace domain depends on input, okay, and X2, which is good for writing a state equation. So what I do is I distributed this transfer function to the other side, okay. S times x1 of s is equal to minus, okay, so I have LA also, minus x1 of s times RA, okay, that's great, plus U of s minus KB x2 of s. Okay, so let's divide it by LA both sides. X1 of s is equal to, okay, minus RA divided by LA x1 of s minus KB divided by LA x2 of s plus 1 over, okay, this is not 1, LA U of s. We have s here. Okay, that's great. That's almost done. Okay, what is this? S times x1, if you take the inverse Laplace, is equal to x1 dot, right? So x1 dot is equal to minus RA divided by LA x1 minus KB divided by LA x2 plus 1 over LA U. What I did is I obtained my first state equation. That's great. That's truly great. Okay, so let's write it here. That's nice. So we will do the same thing for all of the states. Okay, let's clean everything. And now move on to the second state. Okay, so x2 of s, okay, is equal to 1 over jm s plus beta m, okay, torque, but torque is not a state, right? So we don't want to use variables that are not states. So what I do is Ka times x1 of s, that's great, minus, this is x3 of s. Okay, so if I manipulate it like this, let's do it quickly. Jm x2 of s is equal to minus, okay, beta m times x2 of s, that's great, plus Ka, is it Ka? Yes, it's Ka, that's great, we know that, divided by, not divided by, not yet, it will be divided by later, x1 of s minus x3 of s, that's great. Okay, so if we divide everything and find the state equation, we will find that x2 dot is equal to, okay, Ka divided by Jm, that's great, x1, that's great, okay, minus beta m divided by Jm x2, and of course we have minus 1 over Jm x3, this is our second state equation. Okay, let's cut it here, okay, and copy here, because we will later gather them in a state equation format. Okay, that's great. Okay, so let's clean this part and move to the third one, which will be very easy. You will see that this is the easiest part. Okay, so x3 of s equal to kappa divided by s, okay, x2 of s minus x4 of s, right? Because this is x2, this is x4, that's nice. So this is technically, let's clean it here. If I move it s here, and I will find that x3 dot is equal to kappa x2, that's great, plus minus kappa x4. Okay, that's also nice. Let's cut it here. Let's move it here. Okay, that's great. So we are just solving all of the necessary steps. Okay, so let's clean it again and finalize our state equations, finding a state equation for x4. Okay, so x4 of s is equal to 1 over jls plus beta l times x3 of s. Okay, state equation 4 is very easy. If I follow the same path, it is equal to x4 dot, which is equal to minus, okay, beta l divided by jl x4 plus 1 over jl x3. That's great. So we finalize all of the state equations. Now, what are we going to do is technically gather all of them and find a state update equation, and then finalize with an equation. Okay, so x dot is equal to, we have an A matrix, right? So x1 dot depends on x1 minus RA divided by LA. That's great. Okay, it depends on x2 minus KB divided by LA. That's great. It doesn't depend on x3, it depends on x4, it depends on you. So it is equal to 0, 0. Okay, so this is the A matrix. Okay, so we don't have a space for the B matrix, but we will open them later. Okay, so let's move on to the second row. So x1 depends on Ka divided by Jm x1. That's great. Minus beta m divided by Jm. Okay, and minus 1 over Jm, and this is equal to 0. That's great. So we finished the second row. Let's move on to the third row. Third row is easy. 0 kappa 0 minus kappa. That's great. Fourth row is also very easy. 0, 0, 1 over JL minus beta L divided by JL. Okay, so this is our A matrix. Okay, instead of that, just write it as the A matrix. So we compute the A matrix. So B matrix is very easy. Okay, as you can see, x2, x3, x3, x2, 3, and 4, they don't depend on the input. Okay, so I don't need them. Okay, so I can clean them. Okay, so of course we need to make sure that everything is correct. I'm not checking my computations. Beta is equal to, so it depends on u, 1 over LA. Okay, so it is 0, 0, 0. We computed the B matrix. Okay, that's nice. Okay, sorry for that. So this is the B matrix. So if we have A, if we have B, we are now finalize the state update equation, which is in this form: AX plus BU. Okay, what we need is this: Y is equal to CX plus DU. What is our output? Output simply is a state, so we know that D is equal to 0. Okay, D is equal to 0, which is money, and output is the fourth state. So C matrix is simply equal to 0, 0, 0, 1. Okay, that's great. So as you can see, if you have a block diagram presentation, okay, if somebody technically shared it with you, if it's in a specific form where you have first order blocks at most, it can be of course just integrators and gains, then you can technically easily label the signals as your states and then transform it into a state space representation. Okay. Similarly, it's also very easy to obtain a block diagram, detailed block diagram representation from the state space approach, because what's a block diagram? A block diagram is simply a connection between signals, right? And state space is also giving that. For example, x4 is equal to 1 over JLS. Okay, no, it's LS. Okay, so state space. For example, here it says that x4 dot, or integral of x4, is equal to x2 kappa minus kappa x4. Okay, so it's a good practice if you try to find a block diagram representation from a state space representation of a given system.